Analysis of electromagnetic interference (EMI) on steel, water, and gas piping involves understanding the sources of EMI, their effects on the piping, and implementing mitigation strategies. Sources of EMI include power lines, substations, electrical equipment, radio towers, and mobile devices. These sources can induce currents in the piping, leading to several adverse effects. Firstly, electrochemical corrosion can occur. EMI can induce currents in the piping, which can accelerate corrosion. Secondly, electrical interference is a concern. EMI can interfere with electrical systems connected to the piping, such as cathodic protection systems. Thirdly, safety hazards may arise. Extreme levels of EMI can pose safety risks to personnel working near the piping. To mitigate these effects, several strategies can be employed. Physical barriers can be implemented through shielding and trenching. Shielding involves installing conductive materials around the piping to block electromagnetic interference. Trenching involves burying the piping underground, which provides natural shielding. Electrical isolation can be achieved through electrical insulation and grounded connections. Electrical insulation involves coating the piping with insulating materials to reduce current flow. Grounded connections involve connecting the pipe into a proper grounding system to dissipate electromagnetic interference charges. Current averters can be used through bonding wires and surge protectors. Bonding wires involve connecting the piping to surrounding metallic structures to provide an alternative path for electromagnetic interference currents. Surge protectors can be installed on electrical lines to suppress transient electromagnetic interference events. Monitoring and maintenance are also crucial. Inspections should be regularly performed to check the piping for signs of electromagnetic interference-induced corrosion or interference. Monitoring involves using electromagnetic interference meters to measure electromagnetic interference levels around the piping and adjust mitigation measures accordingly. Additional considerations include coordination with utility providers, electromagnetic modeling, and grounding design. Collaboration with utility providers to identify potential electromagnetic interference sources and coordinate mitigation efforts is essential. Electromagnetic modeling involves using computer simulations to predict electromagnetic interference levels and optimize mitigation strategies. Ensuring proper grounding designed to effectively dissipate electromagnetic interference charges is also necessary. References include the National Institute of Standards and Technology, NIST Guide to the Reduction of Electromagnetic Interference from Power Lines, the American Gas Association (AGR), Mitigating the Effects of Electromagnetic Interference on Gas Piping, and the American Water Works Association, or Cathodic Protection of Water Pipe and Tank Systems. Let's delve deeper into each of these aspects. Starting with the sources of EMI, it is important to recognize that modern infrastructure is permeated with electromagnetic fields. Power lines, especially high-voltage transmission lines, are significant emitters of electromagnetic radiation. The higher the voltage, the stronger the electromagnetic field. Substations, which are critical nodes in the electrical grid, also generate substantial electromagnetic interference due to the switching and transformation of high-voltage electricity. Electrical equipment of all kinds, from industrial machinery to everyday appliances, contribute to the overall electromagnetic interference environment. The cumulative effect of numerous electrical devices can create a complex electromagnetic interference landscape. Radio towers and mobile devices are designed to transmit and receive electromagnetic waves, but their transmissions can also interfere with nearby metallic structures. The proliferation of mobile devices and wireless communication technologies has increased the density of electromagnetic fields in urban areas. The effects of EMI on steel piping are multifaceted. Electrochemical corrosion is one of the most concerning consequences. When steel piping is exposed to electromagnetic fields, currents can be induced within the metal. These induced currents can accelerate the corrosion process, leading to premature degradation of the piping. The corrosion occurs because the induced currents create anodic and cathodic regions on the surface of the steel, promoting electrochemical reactions that dissolve the metal. Electrical interference can disrupt the operation of electrical systems connected to the piping. For example, Cathodic protection systems are used to prevent corrosion by applying a protective electrical current to the piping. Electromagnetic interference can interfere with the control and monitoring systems of cathodic protection, reducing its effectiveness. This interference can lead to undetected corrosion and potential failures. Safety hazards are also a consideration. In extreme cases, high levels of electromagnetic interference can create a risk of electric shock to personnel working near the piping. Additionally, electromagnetic interference can interfere with electronic control systems used to monitor and operate gas and water pipelines, potentially leading to hazardous conditions. Mitigation strategies are crucial for minimizing the adverse effects of electromagnetic interference. Physical barriers, such as shielding, involve enclosing the piping within a conductive material that blocks electromagnetic fields. A shielding can be achieved using metallic enclosures or specialized shielding materials. The effectiveness of shielding depends on the material's conductivity and thickness. Trenching, or burying the piping underground, provides natural shielding. The earth acts as a barrier to electromagnetic radiation, reducing the amount of electromagnetic interference that reaches the piping. The depth of burial is an important factor in determining the effectiveness of this method. Electrical isolation is another key strategy. Electrical insulation involves coating the piping with a non-conductive material to prevent the flow of induced currents. This insulation can be applied as a coating or wrapping. The choice of insulating material depends on the environmental conditions and the operating temperature of the piping. Grounded connections are used to dissipate electromagnetic interference charges by providing a low resistance path to ground. The grounding system should be designed to effectively drain electromagnetic interference currents away from the piping. This can be achieved by connecting the piping to a grounding electrode system that meets applicable standards and regulations. Current diverters provide an alternative path for electromagnetic interference currents, diverting them away from sensitive equipment and piping. Bonding wires are used to connect the piping to surrounding metallic structures, creating a network of interconnected conductors that distribute electromagnetic interference currents more evenly. Surge protectors are devices that protect electrical equipment from transient overvoltages caused by electromagnetic interference. They work by diverting surge currents to ground, preventing them from damaging sensitive components. Monitoring and maintenance are essential for ensuring the long-term effectiveness of electromagnetic interference mitigation measures. Regular inspections should be conducted to identify any signs of electromagnetic interference-induced corrosion or interference. These inspections should include visual examination of the piping, as well as electrical testing to measure induced currents and voltages. Electromagnetic interference meters can be used to measure the levels of electromagnetic interference in the vicinity of the piping. This information can be used to assess the effectiveness of mitigation measures and make adjustments as needed. Additional considerations include coordination with utility providers. Utility providers are responsible for managing electromagnetic interference from their equipment. Collaboration with utility providers can help identify potential electromagnetic interference sources and coordinate mitigation efforts. Electromagnetic modeling can be used to simulate electromagnetic fields and predict the levels of electromagnetic interference in the vicinity of the piping. This information can be used to optimize the design of mitigation measures. Grounding design is a critical aspect of electromagnetic interference mitigation. The grounding system should be designed to effectively dissipate electromagnetic interference charges and minimize the risk of electrical shock. Proper grounding design requires careful consideration of soil conductivity, electrode placement, and bonding techniques. The National Institute of Standards and Technology (NIST) provides guidance on reducing electromagnetic interference from power lines. This guidance includes best practices for shielding, grounding, and filtering. The American Gas Association (AGA) offers resources on mitigating the effects of electromagnetic interference on gas piping. These resources include technical reports and recommended practices. The American Water Works Association (AWR) provides information on cathodic protection of water pipe and tank systems. This information includes guidance on the design, installation, and maintenance of cathodic protection systems. In summary, managing electromagnetic interference in shared utility corridors requires a comprehensive approach that addresses the sources of electromagnetic interference, their effects on piping, and the implementation of effective mitigation strategies. This approach should include physical barriers, electrical isolation, current diverters, monitoring and maintenance, and coordination with utility providers. By following these guidelines, it is possible to minimize the risk of electromagnetic interference-induced corrosion, electrical interference, and safety hazards. Furthermore, the selection and implementation of mitigation strategies should be based on a thorough assessment of the specific electromagnetic interference environment and the characteristics of the piping system. This assessment should consider the proximity to electromagnetic interference sources, the soil conditions, the type of piping material, and the operating conditions of the pipeline. Continuous monitoring and periodic inspections are essential for verifying the effectiveness of mitigation measures and identifying any emerging issues. These activities should be conducted by qualified personnel with expertise in electromagnetic interference mitigation and pipeline integrity management. The use of advanced technologies, such as remote sensing and data analytics, can enhance the efficiency and effectiveness of monitoring and inspection programs. Finally, it is important to emphasize the importance of ongoing research and development in the field of electromagnetic interference mitigation. New materials, technologies, and methodologies are constantly being developed, and it is essential to stay abreast of these advancements in order to ensure that the most effective and up-to-date strategies are being employed. The goal is to ensure the long-term reliability and safety of steel water and gas piping systems in shared utility corridors. This proactive approach protects infrastructure, public safety, and environmental integrity. By understanding the complexities of electromagnetic interference and implementing appropriate mitigation measures, engineers and operators can safeguard critical infrastructure assets and ensure the continued delivery of essential services. Let's consider some specific examples of mitigation strategies in action. Firstly, consider a situation where a steel gas pipeline runs parallel to a high-voltage power line. In this case, the power line is a significant source of electromagnetic interference which can induce currents in the pipeline and accelerate corrosion. To mitigate this risk, the pipeline operator might implement a combination of shielding and grounding. The pipeline could be shielded by encasing it in a conductive material, such as a copper mesh. This mesh would block the electromagnetic fields generated by the power line, preventing them from inducing currents in the pipeline. Additionally, the pipeline could be grounded at regular intervals to dissipate any residual electromagnetic interference charges. Secondly, imagine a scenario where a water pipeline is located near a radio transmission tower. The radio tower emits strong electromagnetic radiation that can interfere with the cathodic protection system of the pipeline. To address this issue, the water utility might install filters in the cathodic protection system to block the electromagnetic interference signals. These filters would prevent the electromagnetic interference from disrupting the operation of the cathodic protection system, ensuring that the pipeline is adequately protected from corrosion. Thirdly, consider a case where multiple utility lines are located in a shared trench. In this situation, electromagnetic interference from one utility line can affect the others. To mitigate this risk, the utility companies might coordinate their efforts to implement a comprehensive electromagnetic interference mitigation plan. This plan could include the use of shielding, grounding, and surge protection to minimize the interaction between the different utility lines. In addition to these specific examples, there are several other factors that can influence the effectiveness of electromagnetic interference mitigation measures. For example, the soil resistivity can affect the performance of grounding systems. In areas with high soil resistivity, it may be necessary to install additional grounding electrodes to achieve adequate grounding. The presence of other metallic structures in the vicinity of the pipeline can also affect electromagnetic interference levels. These structures can act as antennas, amplifying electromagnetic fields and increasing the risk of electromagnetic interference-induced corrosion. It is therefore important to consider the surrounding environment when designing and implementing electromagnetic interference mitigation measures. Moreover, the selection of materials for piping and shielding should be carefully considered. Different materials have different electromagnetic properties, and the choice of material can significantly affect the effectiveness of electromagnetic interference mitigation. For example, copper is a highly conductive material that is often used for shielding, while stainless steel is more resistant to corrosion than carbon steel. By carefully selecting the materials for piping and shielding, it is possible to optimize the performance of electromagnetic interference mitigation systems. Finally, it is important to emphasize the need for ongoing training and education for personnel involved in the design, installation, and maintenance of electromagnetic interference mitigation systems. These personnel should be trained in the principles of electromagnetic interference, the techniques for mitigating electromagnetic interference, and the procedures for inspecting and maintaining electromagnetic interference mitigation systems. By investing in training and education, utility companies can ensure that their personnel have the knowledge and skills necessary to effectively manage electromagnetic interference risks. The continuous improvement of electromagnetic interference mitigation strategies requires collaboration between utility companies, researchers, and regulatory agencies. By sharing information, conducting research, and developing new standards and guidelines, it is possible to advance the state of the art in electromagnetic interference mitigation and ensure the long-term reliability and safety of steel, water, and gas piping systems. The ultimate goal is to protect critical infrastructure, public safety, and the environment from the adverse effects of electromagnetic interference.